Well, hello everyone. Today we're going to talk about oscillators. Chapter 16 is oscillators. Um, so that'll be the topic of this lecture. Okay. Um, let's see if I can get this to move here. Um, so oscillators is two main types. One is a feedback oscillator. There's relaxation oscillators. We're going to talk about feedback oscillators first. Okay. Now, we're talking about feedback oscillators first. So feedback oscillators, all oscillators produce a periodic waveform, right? They produce signals. Oscillators are used for generating clocks for microprocessors. They're used for generating carrier signals for radio frequency equipment, transmitters and things like that, and receivers for local oscillators. So it's any device that actually produces a periodic waveform can be considered an oscillator. Feedback oscillators, as the name implies, take feedback from the output and feed it back to the input. So this diagram here sort of shows that. This happens to be an inverting op amp here, which causes the output to be inverted from the input. It comes around through this feedback circuit where it's inverted again and gets fed back to the input. Now it's important, there's two important things here. One is that this inversion happens and it gets inverted again. Now if it didn't get inverted again, the signal, what happens is the signal would die, right? Because it cancels itself out. So you can't have that. It has to be non-inverting all the way around. In other words, 0-degree phase. Matter of fact, it can't even be out of phase. It has to be completely in phase between input and output. The feedback cannot be out of phase, otherwise the signal will go away. The other important thing about the feedback oscillator is that the gain has to be exactly 1, all right, around the loop. So, for example, if the gain is 1.5, then every time it comes around, it's going to get boosted by 50%. And pretty soon you're going to rail your op amp and it's going to stop oscillating. Same thing, if the gain is only 1/2, the signal is going to gradually die out because it's going to get cut in half every time. Right? So it has to be exactly 1 around the loop. Make sense? Okay. This feedback circuit is normally a resonant circuit, a filter of some sort, bandpass filter most commonly, like a tank circuit. We'll see a lot of examples of oscillators as we go through this. A tank circuit's going to allow just one frequency to go through. So it's going to support oscillation at just one frequency. So that's part of the feedback circuit's job, is to make sure that only that one frequency goes through. Now, to get things going, right, we have to have some sort of signal. When you first power up, there's nothing, right? Now, in reality, there's always noise. As you know, something's always going to start the oscillator going. Now, in multisim or simulators, they don't have that, so oftentimes you have to start it using a switch or something. But in multisim, but normal real-life oscillators, you don't have to worry about that. It gets going. The key is, though, is since that initial signal is so weak a lot of times, and your gain is 1, you oftentimes have to put in an automatic gain control circuit, which we'll see here in a minute, to increase the signal, have a gain of greater than 1 before the signal gets going. All right, so it builds it up to a substantial oscillation. Okay. Now the Weinbridge oscillator is a particular type of oscillator. It uses called a lead lag circuit. All right, this is a high pass filter. This is a low pass filter, and it results in this band pass characteristic here. Okay. Now, all of these resistors and capacitors have the same value. In other words, 2 capacitors equal, 2 resistors equal. Okay. turns out the output is going to be 1/3 of what the input is at resonant frequency. All right, exactly 1/3. And the phase shift at that frequency will be 0 degrees. Okay, so we can use that to our advantage. All right, and hook it up into a feedback oscillator like this, who's an op amp. So this is a Wayne Bridge lead lag circuit oscillator. And we feed back, this is a voltage divider, so it gives us a gain of exactly 3, all right, through this circuit, all right. And it's a non-inverting circuit. Notice the feedback comes in through the non-inverting terminal, all right. And we have a gain of 3. So the 1/3 attenuation through the Wayne Bridge is then amplified by exactly 3. So there we have our gain of 1. 3 times 1/3 is 1. And this bandpass circuit only supports oscillation at the 1 frequency. Okay. Now, as I said before, a lot of times when you first start out, you have no signal, or it's very weak. So a lot of times we have to have a gain of greater than 1 initially. All right. So here's a little circuit, a little field effect transistor, which produces an automatic gain control. All right. So if you see this, this FET has now replaced this resistor, the lower resistor here. All right. So you get a gain of greater than 1 when this is turned on initially. All right. Or turned off, and then when it's turned off, because it's a high resistance. Okay. And so once it starts oscillating, all right, it affects this JFET here and changes the gain so that it's exactly 1. Okay, and it charges this capacitor here through this diode, so it negatively charges the capacitor, which shuts off and changes the JFET. Okay, actually turns it on. It actually biases it on. Okay, so that's an automatic gain control for our Wayne Bridge oscillator. Okay, here's a little example. That's our old friend 1/2 pi RC equation. All right, and so the example has 680 ohms and 4.7 nanofarad, resulting in 48.9 kilohertz. Okay. Here's another oscillator, a phase shift oscillator, very clever circuit. It has 3 capacitors and 3 resistors. They're all the same. The resistors are all the same value. The capacitors are all the same value. Turns out when all of these are equal, it attenuates the signal by a factor of 29. Okay, exactly 29. And here's the formula for it. So the resonant frequency is 2 pi square root of 6 RC. Okay, so we have to have a gain of at least 29, of exactly 29, I would say, in order for it to compensate for the loss of the attenuation of 29 here. So RF divided by R3, this is the feedback resistor here, has got to be 29. So here's a little design example. All right. 238K is what RF ends up being. All right. Now we have another oscillator, a twin T oscillator. It has a bandpass filter made up of a low pass and a high pass filters, which are in parallel. All right. Again, 1/2 pi RC. Very simple circuit. By the way, all of these circuits, they're not theoretical. You actually could build them. Matter of fact, we would have built, I think, a Wayne Bridge in our lab if we had it. But yeah, these would all work. These are all real circuits. Okay. Colpitts oscillator. Here's another one. This one uses a inductor and a couple of capacitors. Now, this oscillator and a couple more that we're going to see here uses these inductors. These are often designed on a substrate, PC board substrate, so they may or may not be real oscillators. A lot of times for high frequency applications like radio frequency stuff, radio frequency applications and so on. Whereas the other Wayne Bridge and so on would be used for lower frequency oscillators in the kilohertz, maybe hundreds of kilohertz. The Colpitts oscillators can operate and typically operate up in the megahertz, so a little higher frequency. You recognize the inductor and capacitor combination is a tank circuit. Okay, it's a tuned circuit. Okay. There's a feedback voltage that is generated across C1 down here. All right, and the output voltage is generated across C2 right here. There's V out. The formula for that is 1 over 2 pi square root of LCT. CT is the total of the capacitors. All right. How do we do two capacitors in series? Remember, it's product over sum. So C1 times C2 over C1 plus C2. All right. And here's an equation for Q. All right. There's some homework problems for this. You need to do all those homework problems for all these oscillators. Okay. There's a Hartley oscillator, which replaces the capacitors with inductors, and inductors with capacitors, basically swaps the locations. Similar formula, 1 over 2 pi square root of L1 plus L2, that's the L total. Series inductors are just added together. All right. Now you could put a variable capacitor in here. So you could tune the frequency very easily. You could do that in the other oscillators too. But we'll look at VCOs here in a minute. Variable voltage controlled oscillators. Here's an Armstrong oscillator. This one's kind of important because it uses a transformer. Okay, and the primary of the transformer forms a tank circuit using the capacitor in parallel with the primary. All right, you might recognize this as a very simple common emitter voltage divider bias transistor circuit amplifier. We learned this in Semiconductors 1141. Even has the emitter capacitor here. Difference is the output is fed back to the input. All right, that output supports a frequency determined by the resonant frequency of the tank circuit here formed by the primary of the transformer and the capacitor. So the Armstrong oscillator uses a transformer. Okay. Now the problem with all of these, okay, oscillators up to this point, is they use these discrete components, transistors, capacitors, and inductors, things like that. And these are all subject to temperature sensitivity. Anytime the temperature changes, your frequencies can change. So they're not very stable. So how do you fix that? You probably know the answer. Use a crystal. All right. So here's a modified Colpitts oscillator where we've replaced the inductor with a crystal. All right. Again, we use another common emitter transistor amplifier and just feed its output back to the input through this resonant circuit formed with this crystal. Again, this circuit, you could build it with a 3904 transistor, and you bias it correctly using this resistor divider. It would work. This is a very common circuit, and you could run this in the megahertz. It would work great. This is a very good solid oscillator circuit. Okay. You can look these up online. You can find them and build them there's cookbooks that you can find that have these circuits in them. And if you need a good crystal oscillator, this is a good way to do it. Okay. All right, let's talk about relaxation oscillators. A little different. Relaxation oscillators have a different kind of feedback. And basically, what they are is comparators and integrators, which charge and discharge the capacitor involved using a square wave or triangular wave. Okay, so this actually has both. Has a triangular wave coming out of the V out, and then it gets fed back to this comparator. Okay, and as it crosses zero, the comparator is comparing the output to zero. See, this is to 0 volts. So as this output crosses 0 volts, it's going to switch the state of the comparator, okay, which is going to cause the integrator input to switch between all the way at negative rail to all the way to plus rail. That's how this comparator is working. Okay, it's going plus and minus to the rail. Okay, maybe plus 15 volts down to minus 15 volts. It's at plus 15 volts, this capacitor starts charging, right? And what do integrators do? This is an integrator. What does it do? It produces a triangle wave or a ramp. As that ramp crosses zero, the comparator switches from plus 15 to minus 15, and the capacitor starts charging the other direction. Causes an opposite ramp. So you get this triangle wave here, and then you have a square wave here. Okay. Here's the upper trip point, lower trip point. Okay. Formed by the Schmidt trigger here, R2, R3. We looked at that several weeks ago. Here's an example with some circuit, some component values in it. This is the frequency of the oscillation, okay, and formula. And for these particular component values, you're going to get 671 hertz. All right. And this is what the waveforms look like. Here's the triangle wave on the output, and here's the square wave coming out of the comparator. As it says up here, a 741 op amp will work for low frequencies, okay? But you can use high-speed op amps and get this thing really cooking up into the megahertz if you need to. Not too common, but you can. Okay, this is a novel little circuit here. This is another oscillator. It's a sawtooth oscillator. What is this device here? This PUT. It's a programmable unijunction transistor. That's a mouthful. Programmable unijunction transistor. It's a cool part because what it does is it actually conducts after it gets to a certain voltage across it. Okay, so and it's determined by this VG, whatever this gate voltage is. So you set, let's say, for example, a gate voltage of 1 volt. Well, that might cause the programmable unijunction transistor to conduct whenever the voltage across it, right, approaches a half a volt. Okay, if you want that to have to increase, then you increase your gate voltage, your VG, all right, and it will change the point at which this PUT conducts. This capacitor is charging, right, with this voltage. So the capacitor starts charging, right, gets to a certain voltage. At the voltage across the capacitor that corresponds to the PUT conduction voltage, the PUT conducts and discharges the capacitor, resulting in this sawtooth wave. So you get this waveform that gradually ramps up and then falls right straight down, and then gradually ramps up again, falls straight down. Now the point at which that ramp is interrupted where the capacitor gets shorted out is determined by this gate voltage, this VG, right? Because that'll determine at which point this PUT conducts, right? The point at which the capacitor voltage causes the PUT to conduct, okay? think we have another slide on this. No, they don't. This is a really simple relaxation oscillator. It just uses it's a basic square wave oscillator, which this capacitor charges and discharges based on this feedback. Okay, so let's get this feedback. It's going to charge through this resistor to the capacitor. So, and then we have this, it's basically a Schmidt trigger, okay, where you have an upper trip point and a lower trip point. So this op amp is switching between these two upper trip point, lower trip point values based on R2 and R3. Okay, and every time it switches, it goes to one extreme or the other, one upper trip point, lower trip point. The period of waveform is given right here. This is a super common circuit for generating square waves. All right, very common. The next slide I'm going to show you is a 555 timer, which is used a lot of times to generate square waves. But if all you need is a simple square wave, this is a much less expensive and simpler circuit to use than a 555. So here's your 555. A lot of you know what a 555 timer is. Very common with hobbyists and things like that. You can make all different kinds of things out of 555s. You can make oscillators, which is what's shown here. This is an integrated circuit, okay? It's one part. These are the pin numbers here. This is a pretty good diagram, I think. It's pin 3, pin 4, pin 1, and so on. It has two comparators in it. Has a flip-flop, a set, reset flip-flop, and it has an inverter, an inverting amplifier. This is basically a buffer right here at the end, this triangle. And then it has a transistor in it, okay? The transistor is used to discharge a capacitor. Here's the external part. So we have a resistor, and a capacitor. This forms like a little ladder, if you see. Now notice these comparators are connected up to the capacitor, okay? Internally you have a resistor ladder, right, which generates these reference voltages. So these comparators are referenced. This is referenced to a higher voltage. This top comparator is referenced to a higher voltage than the bottom comparator. Okay, so as this capacitor charges up, each one of these comparators is going to kick in or do something at different voltages. All right, and when they do, they set or reset this flip-flop. And that produces a square wave right here. When that square wave turns on, it turns on this transistor, or goes high, it turns on this transistor, which discharges the capacitor, which causes this voltage right here at the top of the capacitor to drop, all right? And when it drops below a certain point determined by, at this comparator, it'll set the flip-flop. Okay, when it sets the flip-flop, this Q bubble, notice it's inverted, goes low, or it goes high, goes low, and turns off the transistor, allowing the capacitor to charge again. And it'll charge up to the point where this comparator kicks in, which resets the flip-flop. When the flip-flop is reset, this point goes high, which turns on the transistor again, thereby discharging the capacitor, causing it to discharge until to the point where this comparator kicks in and sets the flip-flop again. So that's how the square wave happens on the output here. In the meantime, this waveform here is the top of the capacitor. That's what that looks like. You can look at 555 timer circuits all day long, and you can make so many different things out of them. They have 2 of them in a package. You can get 2 of these in a, I think it's a 16-pin package. You can make sirens. You can make all kinds of annoying things to make horrible noises with them. It's great. We don't use them at work very often because There's just other ways of doing this, usually in FPGAs and things like that. But for a very simple um, oscillator, again, it's an astable multivibrator. That's the fancy name for an oscillator, astable multivibrator. Now, a monostable multivibrator is a one-shot, right? It just produces one pulse based on an input. And you can make that, you turn a 555 timer into that too, okay? Again, there's 555 timer cookbooks you can find, which have hundreds of circuits that the 555 timer is based on, or that is based on the 555 timer, okay? Okay, lastly, the phase lock loop. I know in our other class we talked about phase lock loop. It's a really, really important circuit. It's used in pretty much everything we touch these days. Cell phones and PCs and everything, okay? And basically what it does, its main job is to synthesize frequencies and to stabilize frequencies. That's what's called phase jitter stabilization. And it consists of three main parts, this one does anyway: a phase detector, a low-pass filter, and a voltage-controlled oscillator. Okay, now the VCO could be something just like that programmable unijunction transistor circuit that we just showed. Okay, basically a voltage comes in on the input and controls the frequency coming out. All right, so it's frequency versus voltage. Low pass filter, you know what that is, right? That's going to smooth out any voltage that is going to the VCO to produce a very stable frequency. But this phase detector might be kind of new to some of you. Phase detector's job, okay, is to compare the phase of this F ref input to the F out coming back around to it. So it compares the two the phases between the two inputs here and produces a voltage on the output which corresponds to the phase difference between the two. Now, at 90 degrees, in other words, 90 degrees difference, it produces what I'm going to say the most mellow voltage. All right, it's the lowest voltage. This voltage is actually somewhat of an AC voltage coming out. It's sort of like a triangle wave. Particularly, specifically, it's called the autocorrelation function, but it sort of looks like a triangle wave. But whenever these two phases, which are square waves, by the way, most of the time, sometimes they're sine waves, but for now we're going to say they're square waves. Whenever they're 90 degrees out, this is a very mellow voltage. All right, it's a very small triangle wave. When they're not 90 degrees out, this thing's going up and down and trying to steer the voltage-controlled oscillator around so that it does match 90 degrees on the input. So if this frequency is, let's say, 1 kilohertz, right, and it's not locked up yet, this phase detector is going crazy, just bossing the voltage-controlled oscillator around, telling it, hey, try to match this input. And when it finally does, it locks. This calms down, this output calms down. Low-pass filter calms it down even more, produces a nice stable frequency, and everybody's happy running at 1 kilohertz, okay? If this frequency increases on the input, all right, the phase detector sees that as a phase mismatch, commands the voltage-controlled oscillator to change its frequency to match the incoming frequency. So it's truly a control loop. Okay, so I have 1 kilohertz coming in, 1 kilohertz coming out. What good is that? Okay, it's just like a wire. Well, a couple of things. First of all, if this 1 kilohertz coming in isn't really just 1 kilohertz, maybe it's jumping around a little bit. Maybe it's like some frequency jitter or phase jitter. This low-pass filter, all right, this phase detector can see that, and this low-pass filter is going to filter out the noise, the phase noise coming out of the phase detector, and produce a nice stable 1 kilohertz from your voltage-controlled oscillator, and produce a nice stable F out of 1 kilohertz. So that's called a clock cleaner. It'll take a jittery input and produce a nice, stable, clean output. All right, that's one very common use of a phase lock loop. We use that all the time in video and other broadcast technologies, because they need most of those interfaces need very clean clocks. Other thing you can do is you can put a voltage, not a voltage, but a counter in here, a divider, a frequency divider. So, for example, if your F out is 1 kilohertz, you divide that by half. So now we have 500 hertz, okay, coming into the phase detector. Let's say if 1 kilohertz coming in, coming out, 1 kilohertz produces 500 hertz. What's the phase detector going to do? It's going to say, I only see 500 hertz coming around here. I have to ramp up my voltage on the VCO, so I generate 2 kilohertz here, so that when it gets divided through this imaginary divider here, it produces 1 kilohertz here. So now we have 1 kilohertz going into the phase detector, but 2 kilohertz coming out of the phase lock loop. We've just multiplied our input by 2 in frequency. So this is a very common way of doing frequency multiplication. Okay. Okay, some key terms. We'll finish up with this. Feedback oscillator operates with positive feedback, produces a time-varying output signal with without an external input signal. That's important. No oscillators, unless they're voltage-controlled oscillators, they don't have any external signals coming into them. They just oscillate all by themselves. Then there's a relaxation oscillator, uses RC timing circuits, and they generate square waves and triangle waves and sawtooth waves. Again, no external signal. And then positive feedback is used in these oscillators to sustain the input signal. You need to remember that oscillators need 0 phase around the loop, right? And a gain of exactly 1. Otherwise, they will not sustain themselves. Okay, so that's it for oscillators. If you have any questions or anything like that, you can use our discussion area, and I will do my best to answer your questions. Okay, thank you.